Hello. At the start of the last video, I challenged you to define temperature and showed that this was actually quite difficult to do without invoking circular arguments. Temperature has become mundane, a part of life. We just understand how it is used and the things it refers to, and so we don't really think about what it is too much. In trying to understand how thermodynamics, however, we have to challenge this complacency and try to understand how temperature is mathematically quantified. The first step in doing this is to introduce the notion of the Carnot cycle, as I did in my last video. In that video, I explained how a Carnot cycle can be used to describe the set of transitions that take place in particular special types of engines. I explained how these engines are driven by the changes in state that happen inside the gas inside the pistons within them. Furthermore, I told you about how the gas inside these pistons was a one-component, one-phase system whose state at equilibrium, in accordance with Gibbs phase rule, can be characterized using two thermodynamic variables only. Throughout the previous video, I used the pressure and volume to characterize the state of the gas inside the piston. I thus drew our thermodynamic cycle on the PV plane and explained how the system, on completion of a cycle, returns to the initial thermodynamic state. In terms of the operation of the engine and the set of transitions inside the thermodynamic cycle, I said there were 4 stages. During the first of these, the engine is placed in contact with a heat bath and the gas is expanded isothermally, i.e. at constant temperature. During the second step, the heat bath is removed and the system is thermally lagged, and the gas is expanded adiabatically. During this second step, the thermal lagging prevents heat from being exchanged with the surroundings, and thus the temperature of the gas drops. In the third step, the system is placed in contact with a heat sink, and the gas contracted isothermally. The heat sink is then removed, the thermal lagging is placed around the system once more, and the system is compressed adiabatically so that the temperature of the gas increases. In the previous video, I discussed the amount of heat input and output from the system during this cycle, and the amount of work the engine performs. Doing so allowed me to arrive at the formula at the top of this slide for the efficiency of the Carnot engine. This formula allows me to work out how much work I can get out of my engine by transferring QH worth of heat into it. I then explained why the Carnot engine is the most efficient engine that we can have operating between two temperatures T1 and T2. I did this by showing that if it were possible to build engines more efficient than the Carnot engine, then one would be able to create thermodynamic processes whose sole result was the transfer of heat from something cold to something hot, which I asserted was not possible based on observation of the universe. Last but not least, I alluded to the fact that all of this meant that we could use the Carnot engine to create a common calibration for temperature. Hence, in this video, I'm going to complete this thought and show how this is done in practice. The first step in doing this is to state that a function g of T1 and T2, where T1 and T2 are temperatures, exists that allows us to calculate the efficiency of the Carnot engine that operates between these two temperatures T1 and T2. This is what is done in the formula shown at the top of this slide. We then, for mathematical convenience, define a second function f of T1 and T2 and define this as 1 minus g of T1 and T2 as shown here. We can work out that this function f must be equal to the amount of heat transferred from the gas inside the piston to the heat sink, which is at temperature T1, and it divided by the amount of heat the gas inside the piston absorbs from the heat bath, which is at temperature T2, through some manipulations of the middle term in the equation at the top of this slide. In other words, f of T1 T2 is equal to QC divided by QH. Let's now consider the value of this function f of T1, T2 for three different engines. As shown in the figure in the bottom left-hand corner of the slide, the first of these engines operates between a lower temperature T1 and a higher temperature T2. The operation of this engine is shown by the blue arrows. This engine outputs Q1 joules of heat to the heat sink at T1 and absorbs Q2 joules of heat from the heat bath at T2. The F of T1, T2 value for this engine is thus Q1 divided by Q2, as shown in blue on this slide. The operations for the second of our engine are shown in red here. This engine operates between T3 and T2. It thus takes in Q3 joules of heat from the heat bath and outputs Q2 joules of heat to the heat sink. The F of T2, T3 value for this engine is thus Q2 divided by Q3, as shown in red on this slide. The operations for the last of our three engines are shown in green. This engine operates between T1 and T3. It thus takes in Q3 joules of heat from its heat bath and outputs Q1 joules of heat to its heat sink. The F of T1, T3 function is thus equal to Q1 divided by Q3, as shown in green on this slide. We now note that F of T1, T3 can be calculated by taking the product of F of T1, T2 and F of T2, T3. The factors of Q2 in the numerator and denominator of this product cancel, and one is left with Q1 divided by Q3. This result implies that F of T1, T3 is just some quotient with some new function, capital F, of T1 in the numerator and capital F of T3 in the denominator. This must be the case, as this is the only class of functions we have for which f of T1, T3 is equal to the product of small f T1, T2 and small f T2, T1. The simplest function we can choose for capital F is the identity function. That is to say, capital F of T1 is just a function that returns its own argument T1. This then is the basis of the Kelvin temperature scale, which defines temperature as shown in the bottom right-hand corner of the slide here. In this scale, there is an absolute zero, as any engine that operates between absolute zero and some other temperature is 100% efficient. That is to say, all the heat that is input into this efficient engine is converted into work. Sadly, however, such engines cannot be constructed. To summarize then, we have finally arrived at a universal calibration for temperature. We have done so by considering the operation of a Carnot engine between two temperatures T2 and T1. We have explained that this is the most efficient engine that can be constructed to operate between these two temperatures, and I have explained how this engine functions by absorbing energy from a heat bath at the higher temperature and dumping energy to a heat sink at the lower temperature. We then define temperature using the Kelvin scale, which defines the ratio of T1 and T2 in terms of the ratio of the heat output to the heat sink to the heat absorbed from the heat bath. Thank you for your attention.